Hi guys, and welcome to the latest video in the series on production of materials. In this particular video we're going to look at detecting radiation, the three types that we've been discussing so far. So I guess the first thing we want to have a look at is the fact that there are a number of different methods that are used to detect decay of radioisotopes. It doesn't actually specify which ones you need to know about in the syllabus. It just asks you for multiple methods. So you could include photographic film, the cloud chamber, which we've had a bit of a look at in class, the Geiger-Muller tube, which we've used in class. You can also include things like scintillation chambers, but there's a range of different ones, and as long as you've got a couple, perhaps for comparison, that should be sufficient. So the first one is photographic film, and as you might have seen from an earlier slide, this was the discovery made by Henri Becquerel in the late 1800s, and it was the serendipitous discovery of the fact that radiation, certain substances do emit radiation particles of, or photons of energy, and that can affect the chemicals in film. So I guess the main thing with film is to be aware of the fact that the greater the exposure, the more the film gets exposed, the more fogged it is, or the darker it becomes. The thing with using photographic film is it's very simple and very cheap in order to use as a radiation detector, but it has limited use, because you've got to develop the film to know that it was exposed in the first place, and there's not usually any particular guide to what type of radiation that it was exposed to. So the problem, I guess, with this is that it's a fairly simple technique, and it's reasonably reliable technique in terms of being able to get a result, but it's not necessarily an ideal method. So another method that we can use is the cloud chamber. The cloud chambers are basically made of supersaturated vapors, and this could include alcohol. And as the radiation passes through the cloud chamber, the particles become ionized, and the consequence is they condense into liquid. So you actually can see the little droplets of liquid forming in the vapor, and they make little trails. And these kind of little trails in here are the sort of things that you can see happening when particles ionize those little droplets. So again, this one, because of the ionization required, requires our type of radiation to be an ionizing type of radiation in order for this particular technique to work. Here you can see a few little examples of the types of observations that you might make about the little trails that get left behind when the particles ionize, and you can see the gas condensing in the cloud chamber. It's a nice little effect, and we had a look at a sample of a video in class. Worth having a little bit of a look at that, not to spend too much time on it, just to refresh your memory about what radiation looks like as it passes through a cloud chamber. The one we've spent the most time on, and the one we've used in class, is the Geiger-Muller counter, or a Geiger tube. This is a closed tube, and it contains argon gas. Now we know that argon is one of the noble gases, or inert gases, in group 8 or 18, and therefore it is unreactive. Now in the tube we also have a positive plate on one end and a negative plate on the other end, and this gives us an electric field. And what this means is that if there are charged particles in the field, they'll be attracted to one or the other plate just through electrostatic attraction. So negative particles will move towards the positive plate, and positive particles will move towards the negative plate. At one end of the tube we have a window, and this little window is what allows the radiation to pass through. The idea with the Geiger-Muller counter is that we want the radiation that is passing through to ionize the argon. That's the critical bit here. The radiation must ionize the argon particles, and once they become ionized, then they become positively or negative charged, and then they will interact with the electric field. The electrons will accelerate towards the positive plate because we know the electrons have a negative charge and therefore they'll be attracted to the positive plate. On their passage to the positive plate, they may actually ionize additional atoms on the way. As the charge continues to build, this starts to produce a cascade or a flow of charge, and we can detect that charge through the Geiger-Muller counter because it's converted into clicking. So you can actually hear the clicks, excuse me, and also see it as a digital output, so you can actually see the numbers rising. It's often useful to stabilize or at least control, get a control reading from your Geiger-Muller tube before you start, because there's always levels of background radiation and you want to discard them from your original counts. But then if you record the amount of clicks or the digital count over a fixed time interval for background radiation and then for your alpha, beta and gamma sources, you can get a comparison of the numbers of particles of radiation that are being produced in a certain given standard amount of time. Now, of course, if the electrons have been knocked away from the argons, that will leave argons with a positive charge, and so being positive, they will actually move towards the negative terminal. So you'll get an alternate flow through your Geiger counter of negative electrons flowing in one direction and the positively charged argon cations flowing in the opposite direction. This is a bit of an overview, a bit of a schematic of a Geiger counter. So you can see we have our metal tubing on the outside. We have our power supply, which is going to create a difference in potential between the central electrode here and the metal tube at the outside. So that, and you can see the argon, which is the particles of gas that are present inside the tube. As the radiation enters the little window, it can ionize the gases. So each of these individual argons will become an ion, a cation, and release an electron. And those, of course, will be then taken towards the positive component of this circuit, and the argons themselves will move towards the negative. The counter is actually set up in series with the potential difference with the electrodes, in order that as the electrons are passing through, they will also be passing through the circuit and will be counted. Not a lot of questions that relate to devices used to detect radiation, but in 2008 a very easy question came up. Question number 1, these are the sort of ones you want to get yourself started. Which of the following radiations is measured with a Geiger counter? So you can see the Geiger counter was specifically mentioned, and we can assume that it will be one of the ones that you'll be looking at. And hopefully you realize these lower energy levels of electromagnetic radiation are all incorrect, and the correct answer is A, beta. So thanks for watching.